talking about video games. Zach, a bunch of people are coming in. Start with the bottom. Oh, Tyler Shepard, Jacob Gardner, Stephen Perry, you're here. Cody S. I think I got you already. Yep. Austin, I got you. Okay, I think we're all good. Okay. People are missing are Ibrahim, Nyessa, Abdurrahman, Lane, and I've already done that. And no, there's Lane. John Hardy, Jared, Jordy, Jordan, Zach Schreiner, Fabian, there's Zach Schreiner, and Fabian and Mark. Okay. So this is the final exam review, part 1. I can remember the first time I taught this class. I got done and I was just like completely overwhelmed because I hadn't looked at linear systems since I was in school. I used stuff in the frequency domain. I used stuff in the time domain and never went back and forth between them. I just pushed the button and let the computer do the work. I never looked at them. So I was a bit overwhelmed when I first started writing this exam review, but it got easier with time. But saying that, it's you have to have that time for it to get easier with. Okay. Let's see this, and then we will start with the stuff. Sorry, I was having fun. I'd have fun. COVID has not been fun. My yoga teacher this morning took his first yoga class in a year because he hasn't been able, he's been teaching us through Zoom, but he hasn't been able to actually take a yoga class. So he got Marcy to fill in for him. And it was amazing. He was just laughing so hard. It was unbelievable. There was just 3 of us in the room. So big COVID outbreak possibilities there. We've all been vaccinated. You had the last pre-lecture today. There's no pre-lecture on Wednesday. Homework 12 will be due. The lab will be due on Friday. And then the final exam is Monday, April 26th from 3 to 5 p.m. If you don't show up for the final, you will get a 0 on the final. If you want to take it on Zoom, you can take it on Zoom, where it's all, no, it's not in the engineering building. It will be in Frankie 436 or in my Zoom, one way or the other, the regular classroom. So you can come take it in person or you can come take it through Zoom at the same time, and I will have to manage that. It's getting easier. So grade increasing opportunities. Jonathan, see, that's my other class. I don't know who Jonathan is in the context of this class, so here we go again. Sorry. Jordan, I know who you are. Jordan Ramirez, somebody was chatting at me. I should just leave that down for now. No, you don't have to email me. I will just show up with a whole bunch of exams and waste paper. That's fine. And we're all taking it at the same time. Okay. And that's the big thing. Just because exam week schedule is more packed and it's harder to move things around with people than any other week. And I don't want to have to deal with that. And this is the biggest class I have, and there's like 32 people in it, so I can manage that, I think. The course evaluation receipt is worth 5 points on the final exam. You have about 6 days to finish that. Once finals week starts, they take those down. So go ahead and do that. And then they don't show them to me until a week after finals, until the grades are actually posted. Kind of a good system. You can't get mad at me and give me a bad because of the final, or you can get mad at me for other things, but you can't get mad at me because of the final. And I can't read your reviews and go, oh, I know who that is, and then fail you. Okay, but I wouldn't do that anyways. So the practice final exam is worth 10 points on the final. It's already in BB Learn. A solution that is mostly right has been posted to BB Learn. I think on the first, the alpha and the meg, I think I calculated wrong. You can either turn it in with the final exam or scan and email it to me if you're taking the exam through Zoom. Homework 12, there's 21 bonus points on it. And I will take 1 week of late lab this week only. You have until Friday to turn that in. Just email it to me and you'll get partial credit on multi-week labs. I do reserve the right to lower grade thresholds as I see appropriate. Sometimes, if you get a 90%, you have an A. If you get an 89.5%, I round up, you have an A. If you have an 89.4%, it's up to my discretion where I draw the line. I usually don't draw the line. I mean, if you're really, really close, I usually don't draw the line below you. I mean, and if someone has an 89.35 and someone has an 89.4, I don't really see any real difference between those two grades. Those two people will get the same grade. So I usually draw the line where there's a big gap. In E280 right now, it's between there's two people with an 88.5 and then the next person down is an 84. So that's where the line is. That's easy. I don't know in here until we get all the grades in. We're still waiting for a lot of the labs. 490, so you can actually register for the class now, and there are seats left. The prereq is EE280 with a C or better. It basically covers everything you need from a printed circuit board designer's point of view for putting together systems and understanding the basic analog. Not really touchy analog. I don't even understand some of the touchy analog, but things like, how do I hook this up? If I know the if I have a sensor and I'm putting it into an ADC, what are the things that could go wrong? And how do I make those things go right? So it's more like from that point of view, it's more the basics because that's all I have time for. But it is a class I made up out of stuff that I found important. We've talked about this. It is Monday, April 26th, 3 to 5 p.m. in Frankie 436 or Zoom. And I think I've said that already. But just reiterating, you have to be in one of those two places. And when you show up in Zoom, turn your camera and your microphone on. I will send you an exam. Okay. You get 5 sheets of notes. The 2 sheets from exam 1 would be extremely helpful at this point. And the 2 sheets from exam 2 would be extremely helpful. I didn't delete the part about electronic devices, but yeah, you can use your laptop because never mind. You understand because you have to use Zoom. There are 10 problems total worth a total of 201 points, 15 extra credit points, 5 for the course evaluation receipt, 10 for the completed practice exam. I have a piece of paper. I write down when I get your practice exam and when I write down when I get your course evaluation, and then when you're handing the finals in, I just write down plus 15 or whatever on the front and then add that to your score. So fairly easy. Things to review: the practice final, exams and solutions, the final exam review slides. Exams 1 and 2, I wouldn't necessarily just go right by those because remember we kind of have an abbreviated exam schedule in here. I used to give 4 exams in here. So I haven't covered every possible kind of problem I could put on an exam with exams 1 and 2. It's a little bit heavier on the new stuff. By new stuff, I mean that stuff you have not been tested on before. There's probably about 40 points on BJTs and MOS analog. So go through those review slides. Make sure you kind of like cover that would be the basics to get through this. So this is what I call the mathy part, the first part of the class, and this is what we'll go through today. We did RL, RC, and RLC circuits, and these were our throwing a switch problems, and that would be normally where I would have broken for exam 1. Then we looked at those same switching circuits in the S domain, not something I care about so much, but exam 1, we also looked at Laplace transforms. So if I'm writing a final, I'm gonna say, why is this not doing anything? Draw, pick a color. Okay, so I would probably say a first order circuit, that is RL and RC, or RC, CR, close enough. A second order circuit, maybe a really simple problem. And then that would be RLC. Laplace transforms. Bode plots. Oh, good, that shows up. A Bode plot, fairly simple one. And an S domain circuit. And remember, for the S domain circuits, I like op amps. That's usually where that's usually the first place where people will doing analog design, where you will think they're actually working and doing something. Come on, Hardy. Okay, we got a quorum here now. I'm going back to, okay. So circuits, we looked at diodes, rectifiers, and limiters. I didn't put any rectifiers and limiters on the last one. I put a circuit analysis problem, so that might be a good thing to do. We had a lot of semiconductor physics on exam 1, but that's a possibility. MOSFETs and BJTs, I've already promised you one of each. Oh, we also did standard CMOS. Remember making like AND gates and NAND gates out of transistors? That's a biggie. That's where we're going to start off 380. So MOSFET analog and BJT, yeah, one problem each on those. And then we had physics. So that's about enough for a good exam. It's 200 points, which means there's probably about 10 problems on there. In fact, I have it, I just wrote it today. So I know what I was thinking. I think I did a lot of physics on the last exam, so maybe less on the final. So we want to look at one of these throwing a switch problems. This is first order. The switch has been closed for a long time and opens at t equals 0. We want to find the voltage across the capacitor. We had a methodology for this. We draw the t equals 0 minus circuit. And the switch has been closed for a long time. Did I do this backwards? Maybe. Oh, no, I didn't. The switch has been closed for a long time. So we're sitting here like this. I've got a 24 volt source. Oh, sorry, I have a 15 volt source. 15, not 14. The switch is closed. I have a 4K ohm resistor. I have an 11K ohm resistor. And since my capacitor's been sitting there for a very long time, we can assume it's in its deep C position of being open, but there will be some voltage across it. And that would be VC, not of T, of 0 minus. So the first step is to solve for the initial voltage across the capacitor. We know it cannot change instantaneously. And so this is just a voltage divider here. I've got two resistors. So and the voltage across the capacitor will be the same as the voltage across the 11K. They're in parallel. So VC of 0 minus, which equals VC of 0 plus, is going to equal 15 times 11K over 11K plus 4K voltage divider. And we can get a number for that. So that's 11, that should be 11 volts. So this is 11 volts. I'm trying to conserve space here. Okay, the next step, we want to look at the circuit at t equals infinity. If I do the shorthand version of this, t equals infinity, the switch will have been open. So it opens at t equals 0. So I've got an open switch. That's an eraser. I've got a 4K ohm, an 11K ohm, and now we need to find the voltage across the capacitor. Been sitting there for a really long time, VC of infinity. So it's open again. And this goes back and back to an open circuit. Okay. So the first thing I have to do, I want to find, well, I can find VC of infinity. I can look at this circuit. This resistor has no possible path for current to go through it. It's dangling. It's going into an open switch. Because it's dangling, I can just take it out of the circuit. It needs to be connected on both ends before I consider it. So I've got a capacitor and a resistor. There's no way I can get any, there's no energy source in here. So VC of infinity is 0. And the time constant I can get off of that one too is the REQ that the capacitor sees times the capacitance. And the REQ, because of the 4K being dangling, is just 11K. So this is 11K times what was C? 75 microfarads. It's huge. And when I multiply those two together, this is whatchamacallit. This is my RC. It's 0.825 seconds. So all I have to do at this point, I've got V of infinity, I've got V of 0 plus, I've got V of infinity, I've got tau. I can write an equation for V of t, plugging things in. My V of infinity was 0 plus, my V of 0 plus was 11 minus 0, all times e to the minus t over 0.825. And that will have, it's a voltage, I'll have units in volts, but I'll get rid of the zeros and just clean this up. 11 e to the minus t over 0.825 seconds, and that is in units of volts. So that is my V of t. I can figure out the transient response, how that circuit's going to behave when I throw that switch. That could be, throwing a switch could be something like I've pushed the button on the power supply. It could be I had a MOSFET switch and I have a Arduino that's suddenly turning it on, and we want to see what the transient response is. So that's one problem right there. These source-free circuits, these were your freaky slides. We'll look back at them. Basically what I do here, when I have an RLC circuit, the first thing I do is I determine, is it series or is it parallel? And then I have an equation for alpha based upon that answer, and I have an equation for omega naught. I calculate alpha and omega naught and determine the type of response it has. It can be, there's only 3 answers here, greater than, less than, or equal to. Depending upon that result, I'm either over damped, critically damped, or under damped.
Once I figure out the type of damping, I've got the form of the solution. And remember, this could be a V of T. What just happened? Okay, this could be a V of T. This could be an I of T. It could be power. It could be torque versus time. It doesn't matter. It's a solution to a differential equation. It's whatever variable we're solving for. And I've got different things here. Now, there are variables in here. This one has S1 and S2. So to calculate S1 and S2, we use this equation. S1 is the plus sign. S2 is the minus sign. And yes, it matters. That's the only weird thing you have to remember here. No extra variables here. And the underdamped equation, I would have to go through and calculate omega D to actually find the solution. So the next step was to calculate S1, S2, and omega D as needed. Now you have everything but A1 and A2, and you're going to solve for those looking at the initial conditions. So initial conditions, that's the hard part. If I'm solving for a voltage, this could easily have been I of 0 plus, or power, or resistance. No, resistance is a function of time. Whatever variable I'm solving for here, the initial condition on that variable will give me the sum of A1 and A2 if I'm in an overdamped system. The initial condition on the rate of change of that variable at 0 plus will give me A1 S1 plus A2 S2. We've just calculated S1 and S2. We can find that condition. We have a system of 2 equations and 2 unknowns. Our unknowns are A1 and A2. We can solve for them. Critically damped, you get the first one for free. And the second one you just have to calculate, and underdamped kind of turns out the same way. So you'll need the initial conditions to get those. What horrible thing. Okay. Did I do the circuit? I think I killed you with the circuit analysis part of this on exam 1. And it dumbfounds me every time. It's just like, okay, never mind. I don't want to talk about it. I want to go back and rewrite 188 when I have infinite amount of time. Things in series have the same current. Things in parallel have the same voltage. We know that series, same current, parallel, same voltage. The derivatives of those equations are also true. I'm sorry about this. I know it confuses people, but we did this in the lab. Maybe you're a little better at it now. I don't know. So here is the problem, whole shebang that I've just been talking about. The switch moves from A to B at T equals 0. So we start out in this position right here in position A. We want to draw our circuits. That's step 1. And then we're going to find the, oh, this is the whole really long problem. I've got it on here. Let's do this in the other thingy because I'm going to run out of space. And this is probably the longest problem we will do today. I have it written down here. For T equals 0 minus, what we're going to do is we open up the capacitor. We short out the inductor. There's still a current going through this inductor, and there is a voltage across the capacitor. Those are what we need to find. So let's switch to bamboo paper, and fortunately it begins with a B, and we'll go through and solve this problem. It's probably in the slides too. What the heck is that? Oh, that's 490 stuff. Okay, so the T equals 0 minus circuit. We've talked about this, so I'm just going to do it. 16 amp source is still in there. That switch is closed. The 20 ohm resistor. I have a dangling capacitor And I'm going to draw it in because I have to figure out the voltage here. VC of 0 minus. I'll see what order I solved this in today. This is a 1K ohm resistor. And we have an inductor that's shorted out because it's been sitting there a long time. But since it's a short, it can still have current. Now I have to solve this. I am an electron. I'm coming out of this 16 amp source. And I have a choice of going 3 different paths, through the 20 ohm, through the 1K, or through a short. Every single electron is going to choose to go through the short. And you could calculate that with the current divider rule, but this is going to come out to be 16 amps. I'm going to have no current going through here because it has a much higher resistance, and no current going through here, and no current going through here. So since there's no current going through the 1K and the 20 ohm, there's no voltage across the capacitor. Would be sort of in parallel, but it's not really in parallel, it's dangling. So it cannot accumulate any charge. VC of 0 minus is going to be 0 volts. Okay. We know this also equals, I don't want to do another line for this, IL of 0 plus. The currents, inductors store their energy in the form of a magnetic field, which will keep the current the same. So their current can't change instantaneously. Capacitors store their energy in the form of charge. So their voltage cannot, and the Q equals CV, their voltage cannot change instantaneously. So we've got pretty much everything we can off of that circuit. We're going to draw the T equal, did I do that? Yeah, I did. We're going to draw the T equals 0 plus circuit. Let's go back and look at the circuit to make sure that everyone agrees with me here. Not that one, this one. So let's erase this. We're going to 0 plus, and at 0 plus, the switch is in position B. So all of this is open as far as the RLC network is concerned, so it can go away. So all I'm seeing is an inductor, a capacitor, and the resistor in parallel. So let's go back and draw that. Take the time to draw the circuits. It makes you suddenly see all the things that are, that you know. A resistor and an inductor that's inducting. The voltage across the capacitor is going to be 0 volts. The current through the inductor is going to be 16 amps. Those are the 2 things we know. And we also know the values here. 1K, that's the one that's important. So since they're parallel circuits, the voltages have to be the same. VC equals VR equals VL. And we know VC. So these are all 0 volts, which tells me I have 0 volts across a resistor. Great, we know it's current. So IR is going to equal VR over R, and the voltage across it is 0 over R. So this is going to be 0 amps. This is the basic circuit analysis that I think I got most of you guys on exam 1. We're going to write a KCL equation. It disturbs me, but I'm just going to have to get over it. You'll get better at it with time. The KCL is I've got the currents going into the node equals the currents going out. So I have IC plus IR plus IL has to equal 0. We don't know IC, but we know IR is 0, and we know IL is 16, so that has to be IC equals negative 16 amps. Okay. Reason why we care about this is we can go back into those equations. Where are they? On my cheat sheet. And it's just I equals C dV dt. What we're going to be looking for here is this dV dt and the di dt at t equals 0 minus, because those can be used in my equations. And we know I equals C dV dt. So if we evaluate this whole thing at t equals 0 plus, this is why mathematicians hate me. It's the whole thing at t equals 0 plus. It is I of 0 plus over C is going to give me dV dt at t equals 0 plus. If I want, what's the other one? L di dt must equal V. We evaluate this whole thing at t equals 0 plus. Notice I'm making it my notation. So V of 0 plus over L is going to be di dt at t equals 0 plus. We can use those equations and then use those as our initial conditions. Those are the initial conditions we're looking for. So back to bamboo paper. I did my little mathematical aside. What do we know? We know I of 0 plus, IC, did I freeze? No, this is the wrong program to do that. IC of 0 plus over C is going to be dV dt at t equals 0 plus. And we may need that one. I'm going to circle these. These are the one, I circle the things that are going to show up again. This one right here. And my dV dt, I of C, what was IC? It was negative 16 amps. Over C. What the heck was C? Now I need to know what C is. 20 millifarads, 0.02 farads. And so that comes out to be, did I even do that? No, I didn't, because I didn't need it. I didn't need it to solve the problem, and I was like, but you might need it to solve the problem if it was a different problem. 16 divided by 0.020, and that gives me 800. 800, it's going to have units of amps per second. It's a, wait, that's dV dt. It's going to have units of volts per second. And it's got a negative sign on it. So that is one that we may show up later. The other one we can find VL of 0 plus over L will be my di dt at t equals 0 plus. And that's the one that we're actually going to use. And that will come out to be 0 because it's 0 over L. And it will have units of amps per second because it's a rate of change of current. Okay, that was the circuit analysis part that threw everybody off. Wouldn't that be great? We want to figure out what our alpha and omega are. And we know we can go back and look at that circuit. And if we look at this circuit, this is parallel. So I'm going to use the parallel equations. And they're on that sheet for parallel at t equals 0 plus, alpha equals 1 over 2 RC, and omega naught is always 1 over root LC in life, the universe, and everywhere. Every circuit I've ever seen. And when we calculate that, we end up with alpha, we just plug in numbers, is 25 millinepers per second. And omega naught is 10 radians per second. We'll just pretend that they're the same thing since they're dimensionless units anyways. And I don't get high strung over that anymore. So this is 10 radians per second. Clearly omega naught is bigger than alpha. And we go back to that table and that tells us it is underdamped. So this is a big milestone in here. Because once you know it's underdamped, you can go back, to this, and you say it's underdamped. Here is the form of the solution. What am I solving for? I asked you to solve for IL of t. So I'm going to write down the form of the solution. This is the form, and I always word it like this on the exams, and some people just don't get this part. Form of the solution. I just copy it down. This is the easy part. So IL of t is what we were asked to solve for. Has to have this form. A1 cosine omega dt plus A2 sine omega dt, omega dt, all times e to the minus alpha t. We've already solved for alpha. We know A1 and A2 are on the horizon. So let's go for omega d. And also right here, it says omega d. There's a little formula for omega d right there. And I'm going to use that one. My little cheat sheets. Omega d, square root of omega naught squared minus alpha squared. If it comes out to be negative, you've done something wrong. It will be a real number. What was omega d? It's 10 nepers per second because alpha was really small. Okay, so we got that for the equation. Now we want to go back and look and see for an underdamped system. For an underdamped system, I've got this system of equations right here. It says V of 0 plus, but we're not solving for V. We're solving for I. So this will be IL of 0 plus. And this will be DIL dt at 0 plus. So IL of 0 plus is A1. Sorry, this is like the worst part for me. I just have to survive. IL of 0 plus is A1. And the thing is, I'm actually good at math. I just hate getting all the symbols right. I can think math. I can't make math teachers happy. And we've solved for IL of 0 plus. IL, that's IC. IL of 0 plus is 16 amps. It's right there. It's got a box around it. So this is 16 amps. And the other equation that we're looking for, and I just know this because I wrote it down, IL prime, the derivative of IL at 0 plus, is minus alpha A1 plus omega D A2. So we've got all those numbers here. So alpha was really small, 25 milli. A1 was 16. Omega D was 10. And we don't know A2. But we do know our IL prime of 0 plus. It is right here. It was 0. Yay. So all this equals 0. We can solve that for A2. And A2 is 40 milliamps. Now we just have to go back to the form of the solution and plug in everything we know. I need to change colors. And I need make it something really red, contrasting. So A1 was 16 amps. Oh, that is not contrast. Love technology. 16 amps cosine omega D. Where the heck was our omega D? It was 10. Plus A2 is 40 milliamps. We could just write that as 0.040 sine 10t times e to the minus 25 milli t, or 0.025 t, and that will be in amps. There's our solution. We just plugged everything in. Thank goodness. If I put the whole thing on, I usually put parts of the problem on the test. If I put the whole thing on it, it'll be a relatively simple problem to solve. I'm thinking 10 minutes. Let's see, 10 problems. 10 problems. You get 2 hours, so that's 120 minutes. You get about 12 minutes per problem. And some of them will be shorter than others. And this will be, something like this would be the longest thing on there. Okay, somebody's talking to me. No. Jordan, if you turn in a practice final and I deem that it weighs enough, it's worth 10 points. It's not, I'm not going to spend a lot of time grading them. I'm going to just look through it and just see if you finish. You have the solution. So it's not like, yeah. Just if you copy the solution, that's your own problem, because then you haven't learned anything, and then you have to come and take the exam. As long as you, the only time the only time I ever docked anybody on the practice final exam was the 2 kids in EE110 who had the brilliant idea of printing out my solution, scratching out the word key, and writing their name on it. This is why freshmen don't last very long. Allergies. Okay. Laplace transforms. You have these tables. They should be on the note sheet for exam, whatchamacallit, exam 1. Basic stuff. You just basically, we're looking these up. We're not solving the integrals. You get to do that in 348. And we've got some properties here. We'll refer back to these. I think I'm just assuming at this point you are somewhat familiar with them. So I've got something that looks like e to the minus something t cosine 9t. So I go back to the table and I look for that. E to the minus, was it a sine or was it a cosine? It was a cosine. E to the minus at cosine omega t is going to transform into s plus a over s plus a squared plus omega squared. So I just find the number here, I plug in the a, the s is the variable, I plug in the omega, I find the omega here and I plug it in. That one's fairly straightforward from that property. And this would be s plus 7 over s plus 7 squared. My alpha is 7 and my omega is 9, so plus 81. I'm just going to skip this one because I really haven't done that with you guys this semester. I wouldn't put it on an exam. It's more horrible than you can than it looks like. Okay. I've got t to the fourth e to the minus 3t. I go back to the table and I find something that looks like this. T to the n, e to the minus alpha t. This is straight off the table. Is n factorial over s plus a to the n plus 1. So I just figure out the numbers. My n is 4. So this would be 4 factorial, 4 times 3 times 2 times 1, over s plus a. A is the thing right here, 3. S plus 3, and to the n plus 1 power to the 5th power. So this would be 21 over s plus 3 to the 5th power. Now the next one looks really bad. You don't have to take the derivative. That's the magical thing about, this is why we like Laplace transforms. This is why we use Laplace transforms as a shortcut way to solve differential equations. And by the way, differential equations is the only part of calculus you'll ever need as an engineer. But you had to take the rest of it to get to differential equations. That would be another thing I would love to rewrite. Okay. I'll get my PhD and I'll just write a bunch of textbooks. Say, why have you been torturing these kids for so long? Okay, here we go. Where is it? It is properties. If I want to take the first derivative of something in time, what I can do is just take the Laplace transform of the original function, multiply it by s, and subtract off the initial condition in the time domain. We've already found the Laplace transform of the function. We did that in the last part. So that one is right here. So what I need to do is take, that's 24, not 21. We need to take that and we need to multiply it by s because, yeah, I just showed you that. So I take s, I multiply it by this thingy, and I subtract off this function at 0 minus, or 0. It doesn't really matter that much. 0 minus or 0 is going to be pretty much the same thing. So if I plug in 0 here, t equals 0, I get 0 to the 4th times e to the minus 0. Well, e to the minus 0 is 1, but 0 to the 4th power is just 0 multiplied by itself 4 times is still 0. So this is 0. So all I've done is it's the last step, multiplied by s. You don't have to do the calculus. Anything in here that involves you taking a derivative, it's probably, I didn't mean for you to do that. Although after teaching for 10 years, I can actually do derivatives again in my head. Okay, when we want to take the inverse Laplace transform of something, we did something called a partial fraction expansion. You may have to do that. There's not an evil one on the exam. It's something like this. There's no squared terms in there. So if I want to do this, it's a over s plus 1 plus b over s plus 3. And we can use residues for these simple factors. So a is just going to be s plus 1. I'm sorry, I'm just railing through this. F of s, evaluated where this factor goes to 0. So that would be at s equals negative 1. So I go back to this side of the equation and I plug in 4. My s plus 1 gets canceled out by this s plus 1. And then I get over s plus 3, which is negative 1 plus 3 is 2. So this is 2. My b is just going to, and your calculators can do this. And if you do it on your calculator, make sure you know what you're doing, because if you get it wrong and just write the answer down, I don't give you a lot of credit for it. So that would be B. It's going to be 4 again, and it would be, but now instead of that term canceling out, this term would cancel out. So it would be -3 plus 1 is -2. This would be -2. And so I know this is A is 2 over S plus 1. I've got it into terms that look like what's on that Laplace one. And I even know this one. The Laplace transform of 1 over S plus alpha is going to be e to the minus alpha t. So I transform this part. I have 2 e to the minus 1t minus 2 e to the minus 3t. And I take the whole thing and I multiply it by u of t, just to remind myself my domain is t greater than 0. I know nothing about the function for t less than 0. One of the shortcomings, well, not a really big shortcoming, because you can define your t equals 0 to be the point in time when you start caring about things, but it's one of the mathematical shortcomings of Laplace transforms. You don't know anything about time before your event. Drawing Bode plots. Do I just have to do this all over again in like condensed form? Tomorrow, on Wednesday, we will do the circuit part of the class. And the part I've kind of dedicated my life to, circuits and physics and things like that. This is kind of a really important key slide. If you have these functions, I did not put a Bode plot on exam 2. There's probably one on the final. But it should be a fairly simple one. What we do with these Bode plots is we plot each of the factors using this chart, and then we add them together. I'm not going to go through all the mathematical justifications for why we can do that. Just remember that you can do that and add together. Okay. Let's do one that is like, oh, here we go. But we're not doing that one. We're doing the one on the previous slide. I don't even want to do that one. 1,000 s over s plus 100 squared. Did I freeze? No, I didn't. 1,000 s over s plus 100 squared. Now remember that we have to put it into standard form. So our standard form looks like this: 1 plus s over omega naught. So I've got to get it into that form before I actually do the plot, before I even attempt to do anything. So in order to get rid of this factor of 100 in here, I would have to take 1,000 s, and I would have to factor out 100 to get rid of it in one term, and I'd have to do that twice. So I multiply that by 1 plus s over 100 squared. I did this. This is the part that confuses people. So I have something like s plus 100. I could factor out 100. And then I would have s over 100 plus 1. Right? Now, if I had s plus 100 squared, I would have to factor out that 100 twice, because it's like s plus 100 times s plus 100. So I'm going to put 100 squared there. Okay. Yeah. It's kind of like 188. The math teachers don't teach you the math that's important. And the 188 teachers don't teach you the circuits that are important. And so I just have to go back and yeah. There's a lot of really elegant circuits in 188 that I see no purpose for. And it really bugged me for a while. And then I went back, and my dad originally started to college in 1939. And then World War II happened, so he graduated in 48. He was in England for a while bombing things. I went back to his original electrical engineering textbook, and I went through it. And suddenly it made sense, the circuits that you see in the 188 book. They are things that were like bias circuits for vacuum tubes and things that people would have used in the 30s. And no one's thought to change them. And so when it comes to modern circuits, you've got your head full of this vacuum. They've taken the picture of the vacuum tube out. But it's not. You need to go into like basic transistor circuits, op amps, and yeah. Without doing all the theory and stuff. Just, okay, never mind. Get off my. So anyways, when I simplify that further, I've got 1,000 over 100 squared. This is going to be 0.1s. I'm going to write it over here because I don't want it. 0.1s over 1 plus s over 100 squared. I was trying to get Sam Proof to rewrite it, but I nearly had him convinced to do the work. We've got 3 factors here. So I've got this k is the constant term, and it's 0.1. It's not 1,000. K equals 0.1. So in order to find that in dB, I need the 20 times the log of 0.1, which should be negative 20 dB. So I'm just going to draw where my k is right here for make this negative 20. This axis is labeled, so I'm going to label it. This was h, so this is the magnitude of h of s, and the units are dB. This one's labeled for me. So minus 20, we'll make this minus 60. Go down, make this minus 100. We'll make this plus 20, and go up 2 more and call it 60. So my k is at minus 20 dB. We have a line for that. I have another factor here. Let's change colors. Something that will show up on purple. How about gray? Okay, so I've got another factor here, this S. The S, if we go back to that chart, this is like a 0 at the origin. No, I did not freeze, thank goodness. I don't want to freeze in the middle of my Bode plot. Origin, because I have to do it all over again. Okay, and if we look at the chart here, a 0 at the origin passes through 0 dB, if you can read that, and at omega equals 1, and it has a phase shift of 0. I didn't ask you to do the phase shift, so you don't have to worry about that. I haven't asked anybody to do a phase shift on an exam for a long time because it's hard enough to grading these. Okay, oh no, we don't want to talk about that. Okay, so it's going to pass through 0 dB, which is right about here at omega equals 1. And because it's a 0, it's going to have a slope of positive 20 dB per decade. So every time I go up a factor of 10, I'm going to go up 20 dB. And I can just draw these points on here. It's going to be a straight line. And I've got a point and I've got a slope. And there is my 0 at the origin. Okay, one more factor. And I'm going to treat this like it's one factor, even though it's squared. Purple, let's go light blue. Oh, that's too close. Let's go light green. Okay, so I've got my 1 plus s over 100 squared. And this is like having 2, and it's in the denominator, so it's a pole. It's like having 2 poles at omega equals 100. And we go back to our little chart thingy. And this is a simple pole. It was a pole, yeah, it's in the denominator. So it's going to be 0 dB until I get to omega naught. And then it's going to fall by minus 20 times n, and n is the number of poles per decade. So we got that in our head. And then we go back and we say, okay, so it's going to go 0 dB until I get to omega equals 100. And then it's going to fall, since it's squared, it's going to fall by 40 dB per decade. So 40, 40, we have that plot. Now we have one more thing left to do, and that's add up all the pieces. The simplest way I can explain to you how to do this, what am I running out of colors here? Let's do purple. We can do purple on here. We're going to add up, like at this 0.01 radian per second. We've got 0 dB, minus 20, minus 60. If I add all those up, I get minus 80. And then I go to 0.1. I've got 0, minus 20, minus 20 twice. So this is minus 40. Is that right? I said minus 60 and I plotted it at minus 80. Okay. At 1, we've got 0 plus 0 minus 20 is minus 20. At 10, we have 0, we have positive 20, negative 20, yeah, that adds to 0. And this is going to keep going up by 20. When I get to here, I've got a slope of plus 20, a slope of minus 40. It should start falling, but we can add it if we wanted to make sure. We've got 60 minus 40 is 20, minus 20 is 0. So we're back down to 0. And that other point's going to end up being right here. So there is our composite graph. It looks like what I could use this for is this might be something that would be a good filter for not a good filter. It would be a bad filter for a power system. We had something that only had like power at 60 hertz, which would be right about in here. It would pass the 60 hertz and it would attenuate everything else. But it's not a very good filter, but I do see a purpose for this. Okay. All right, that's not hertz, that's in radians per second, never mind. Bode plots, okay. Last thing we talked about was these circuits in the S domain. Usually what I care about, and you can define your t equals 0 anytime. So where you tend to define your t equals 0 point is where you turn the power on or something happens. As far as the model of an inductor goes, we talked about if there is initial energy in the system, you do have to add this parallel source that it's just basically modeling the initial conditions. And I need to change colors. Initial conditions. But if the initial conditions are 0, we can just model the inductor as L times S. It's like J omega L back from 188. Same thing with the capacitor. We can make this 1 over SC in the frequency domain if it doesn't have any initial conditions on it. Sometimes you have them and you have to worry about them. I've never put anything like that on an exam. We did solve this one. I don't want to do that one again. This is probably the best circuits in the S domain problem to review for the final exam. The op-amp problem on exam 1, which is sort of similar to homework 6 problem 1. Big things you're going to have to do there, and most people did fairly well on it. You get an op-amp circuit, and I usually give you an inverting one. And we just call this ZF. This here is called ZS. And ZF and ZS may be resistors. They may be parallel or series combinations of resistors and capacitors. You're never going to use an inductor in an op-amp circuit. That just is a stupid thing to do. Don't even. It's like the 188 circuits. Don't think about it. But they're just going to be there like this. And this is V out. And this is an inverting op-amp, so we're going to get rid of that ground here. Got rid of more than I wanted to. We're going to put some kind of signal source right here. And people have solved this circuit so many times that they've memorized. Memorized this. The ratio of V out to V sig is going to be negative ZF over ZS. Given that equation, can you calculate ZF? Can you calculate ZS? And can you plug it into that formula? The algebra is not nearly as bad as it was on exam 1, which wasn't all that bad to begin with. And ZF, yeah. And capacitors, impedance of a capacitor is minus 1 over SC. The impedance of a resistor is R. Plug it into those formulas and just and maybe sketch a little Bodie plot of it. That's about it. And that's all I can. And I'm glad I had 2 days for this because I would have been flying through this otherwise. Part 2 is the circuit part. Yeah. What I've done with my life, the circuits, the physics underneath the circuits, and the infrared, RF, and optical transmission of power, or voltage or current, whatever you want to call it, photons. It's time to stop. Any questions? Who isn't here? Jared and Jordy. I want to go back and play video games now. There's donuts in there too. There's donuts and video games. Okay, it's finals week. We're not supposed to have any IEEE meetings this week, so it's not an IEEE meeting. It's 6 guys and the IEEE advisor hanging out in the IEEE room. Oh great! What did I do? And yes, they are capable of helping you with your homework too. We came up with all kinds of wonderful things. The lights were too bright on the screen. We only have 1 light switch in the room. So the engineering solution was somebody stood up on a chair and pulled light bulbs out. Hunter's gonna be so mad at us. It does. I know, but today's the 16th, right? Monday. Question mark. I don't know. I do have my glasses. What? Oh, they're in my office. If you want to go back with me, I can give them to you. I forgot to bring them. That's a good point. I forgot about those again. And anytime you want to come into the IEEE room, feel free to knock on the door, or you can email me and I can get you your own key code. Actually, the most fun we had in there was when Fallon was president. And she was, wow, okay. Okay. we had all kinds of fun stuff. We actually did activities, and she'd decorate the room. And I'm just going to stop this now.